Welcome to the Deep Dive, the show that really cuts through the noise, all that information out there, and gives you the clearest, most impactful insights. If you've ever felt just buried under articles, documentation, maybe even your own notes, wondering how to pull out what really matters, then you're definitely in the right place. We're here to give you, well, that vital shortcut to being genuinely well informed, without the usual information overload. Today, we're embarking on an exciting deep dive. We're going right into the very foundation of Python programming. Think of it like peeling back the layers, really understanding the core building blocks that make everything else possible in this incredibly versatile language. We've got this comprehensive stack of notes on Python fundamentals. It covers everything, really, from basic data types all the way to the sophisticated ways data gets organized and managed. So our mission for you today is pretty clear. We're going to extract the most important nuggets, clarify any, tricky concepts, and really equip you with a solid intuitive understanding that goes beyond just memorizing syntax.
And what's truly fascinating about this journey, this look into Python's fundamentals, is that it's not just about learning syntax or like a list of features. It's really about developing a profound mental model, understanding how information is represented, how it's processed, organized, in a way the computer can actually understand and work with. This knowledge isn't just academic, right? It's the absolute bedrock for building any kind of software. I mean, from the simplest script that automates a little task to the most complex large-scale applications. Mastering these core concepts, it truly empowers you to think like a programmer. It gives you the clarity to design elegant solutions.
Okay, so let's unpack this. Let's just jump right in. When you write any piece of code, any code at all, you're constantly working with different kinds of information. Could be a name, a number, maybe a true-false decision. Python, well, like any robust programming language, it needs to know exactly what kind of data it's dealing with, which brings us straight to the first crucial set of building blocks, Python's core data types. Let's start with numbers, specifically integers and floats. Integers are, your whole numbers, positive, negative, or zero. You use them for things like counting items, tracking ages, representing discrete quantities, so something like age 30 or maybe quantity equals 5. Those are classic examples. Floats, on the other hand, well, they're numbers that include a decimal point, used for quantities that aren't whole, like price, 99.99, or, pi equals 3.14159.
Precisely. And for anyone familiar with other programming languages, Python's integers have this crucial, often quite surprising advantage: arbitrary precision. Now, this isn't just some quirky feature. It fundamentally changes how you can approach numerical tasks in Python. Imagine not having to worry about integer overflow errors, the kind that plague languages like C++ or Java, where you can fix maximum size pretty quickly. Python just silently handles numbers so vast they break many other systems. For instance, calculating something like 2 1,000, that's 2 raised to the power of 1,000, it results in this, well, astronomically large number that Python just handles effortlessly. No special libraries needed. This is a huge liberation, really, for fields like cryptography or large-scale simulations, financial modeling, anywhere precision is absolutely paramount, and dealing with massive numbers is routine. It kind of highlights Python's underlying philosophy, doesn't it? That even a number is an intelligent object that can adapt to what you need.
That's a fantastic point about Python's inherent power with numbers, really sets it apart. Now, what about operations that involve both integers and floats? How does that work?
Okay. If we connect this to the bigger picture, when an operation involves both an integer and a float, Python automatically promotes the integer to a float, and the result is always a float. This is a deliberate design choice. It's there to prevent data loss and ensure precision. So if you perform, say, 5.0 plus 2, the integer 2 is temporarily treated as 2.0. The result you get back is 7.0. This automatic conversion, it's subtle, but it's a really powerful feature. It's designed to help you avoid unexpected truncation or, precision loss that might happen in languages with stricter type rules. It just simplifies numerical calculations, letting you mix types without constantly needing explicit casting.
Okay, makes sense. So moving on from numbers, let's talk about strings. Strings are basically sequences of characters, any text you want to represent in your head. And they're incredibly versatile. You can define them using single quotes like hello or double quotes, world. That's pretty standard. But you can also use triple quotes. This is a multi-line string. These are super handy for text that spans multiple lines or maybe contains internal quotes without needing to escape them all the time.
Right. And the true power and versatility of strings really comes alive with their rich set of built-in methods for manipulation. Python offers tools to change the case, like .upper or .lower, essential for standardizing text input, for instance. Methods like .strip are just invaluable for cleaning data. Removing unwanted leading or trailing white space. That's a common nuisance when you're processing user input or reading from external files. Drist handles it perfectly. Then you've got things like replace old new to swap parts of a string, or split to break a string into a list, maybe based on spaces or commas. Imagine you're processing usernames. You might have something like userinput.strip.lower.replace. That gives you a clean, lowercase, hyphenated username for your system. It's concise and incredibly powerful for preparing data.
And speaking of powerful and concise, this is where F-strings truly shine. Formatted string literals, I think, is the official term. They are definitely the modern, very readable way to format strings. You can integrate variables, even simple expressions, directly into the string. So instead of all that cumbersome concatenation or the older format methods, you just put an F right before your string. Then you embed variable names directly inside curly braces, like F, my name is name, and I am age years old. It just makes your code so much cleaner, so much easier to read. It dramatically improves readability, really. It's a huge step forward for string formatting in Python. A real quality of life improvement for any developer, I'd say. Okay, finally, for the basic types, we arrive at Booleans. These are maybe the simplest, yet possibly the most fundamental data type for logic and decision making in any program. A Boolean can only hold one of two specific values, true or false. That's it. They are the absolute core of all logical operations and conditional statements. They dictate whether certain code blocks run or not, essentially guiding the flow of your program.
Building on that, what's often surprising, especially for new Python programmers, is this concept of truthiness. While true and false are the explicit Boolean values, many other Python values can be interpreted in a Boolean context. For instance, an empty string, that's considered false. The number 00 is false. An empty list or an empty dictionary, also false. Conversely, non-empty strings, any non-zero number, and non-empty collections are all considered true. This concept of truthiness is, well, it's a fundamental Pythonic idiom. It allows you to write incredibly elegant and concise conditional statements. So instead of writing if len_mylist 0, or maybe if mistring goes to 0, trying to write if mistring miles, you can just write if mylist or if mistring. This subtle power is what makes Python code so often readable and succinct, especially for experienced programmers. It lets you focus on the logic, not the boilerplate. It's a really key part of Python's expressiveness, simplifying a whole lot of conditional checks.
Okay, so we have these different types of data. What does this all mean in practice? Once we have our data, numbers, text, truth values, we naturally need to do things with it. And that's exactly where operators come in. They're kind of like the verbs of our programming sentences, letting us perform calculations, make comparisons, assign values, and so on. Let's kick off with arithmetic operators. These are the real workhorses for numerical stuff. You've got plus for addition, for subtraction, for multiplication, and for standard division. These are your everyday tools for calculations. Pretty straightforward, absolutely essential.
Right. And beyond those standard four, Python offers a couple of incredibly useful ones that might be new if you're coming from, say, a different background. Those are for floor division and percent for modulo. Floor division is crucial when you need a whole number result. It discards any fractional part, always rounding down. So, for example, if you have 25 apples and each pie needs 4 apples, 25/4 gives you 6, meaning you can make 6 complete pies, perfect for calculating batches or maybe pages of content. The remainder operator, or modulo percent, tells you what's left over from a division. So 25% 4 gives 1. You'd have 1 apple remaining. This is incredibly useful for things like checking if a number is even or odd, number percent 2 equals 0. Or for cyclic operations like rotating through a list of images or figuring out if a task should run every n iterations. And something really vital here is understanding operator precedence. You need to know the order Python performs these operations to avoid subtle bugs where your calculations just don't add up like you expect. It generally follows the standard PEMDAS or BODMAS rule. Parentheses first, then exponents, then multiplication and division, which are evaluated left to right, and finally addition and subtraction, also left to right. For instance, 5 plus 3, 2 gives you 11 because multiplication happens before addition. But if you want the addition to happen first, you explicitly control the order using parentheses. 5 plus 3, 2 yields 16. Using parentheses makes your intentions crystal clear. It prevents those unexpected mathematical outcomes in your code. Always a good idea if there's any ambiguity.
Okay, clear. Next up, we have comparison operators. Their purpose is pretty straightforward, comparing values. And the result of any comparison is always a Boolean value, either true or false. These include for equal to, for not equal to, for greater than, for less than, for greater than or equal to, and for less than or equal to. You might use these all the time, like checking if age 18 to verify eligibility, or if quantity before trying a division to avoid an error. They're fundamental for making decisions in code.
Yes, and a critical best practice here, really crucial, is to compare values of the same data type, or to explicitly convert them to a common type first. This avoids unexpected results, or worse, errors. Type matters immensely. For example, 5 equals 5. That's false, because one is an integer, the other is a string, even though they look like the same numerical value. Python sees them as distinct types. And even more critically, trying something like 510 in Python 3 will actually raise a type error. You just can't directly compare an integer and a string with less than or greater than operators. You need to convert one to match the other first, maybe like 510. So always be acutely mindful of the types you're comparing. Overlooking this can lead to silent bugs or runtime crashes.
Got it. Type safety is key there. Okay, moving on to logical operators, and, or, and not. These are used for combining or modifying Boolean expressions, letting you build up more complex conditions, and returns true only if both operands are true, or returns true if at least one of the operands is true, and not as simple, it just flips the Boolean value of whatever follows it. So not true becomes false, and not false becomes true. These are really the bedrock of building complex decision trees in your programs.
Absolutely. And what's incredibly powerful and efficient about Python's logical operators is something called short-circuit evaluation. For, and, or. For and, if the very first condition evaluates to false, Python immediately knows the entire expression has to be false, so it doesn't even bother checking the second condition, it just stops. Similarly, for or, if the first condition is true, Python knows the whole expression must be true, so the second part is never evaluated. Now, this isn't just a performance optimization, though it can save computation time. It's also a critical error prevention mechanism. Consider code like isUser and user.isActive. If user happens to be none, which, as we discussed earlier, is false in a Boolean context, the second part, user.isActive, is never called. This perfectly prevents an attribute error you'd otherwise get if user was none and you tried to access its summarily active method. This pattern is incredibly common and really crucial in writing robust Python code.
That's a really neat safety feature built right in. Okay, and finally for operators, we have assignment operators. The most basic one is just the single equal sign, used for assigning values to variables like x equal 5. Simple enough.
Right, but Python also offers these things called compound assignment operators. They're incredibly convenient shorthand for updating variables. These include plus, makes, modulus, for exponentiation, modulo, and tains. For example, writing x plus 3 is functionally exactly the same as writing x plus 3. Now, these aren't just about making the code shorter, though they do that. They often lead to more readable code for repeated operations, especially when you're accumulating values. Think about total plus item price versus total plus item price inside a loop. The compound version plus is much clearer about its intent. Total is being incremented. They just make your code more expressive and honestly often reduce the chance of typos too.
Okay, this is great. We've got our individual pieces of data. We know how to operate on them. But what if we only want to do something if a certain condition is met? That happens all the time. Or what if we need to repeat a block of code multiple times, maybe until something specific happens? This is exactly where control structures come into play. They direct the flow of execution, allowing your program to make decisions and perform repetitive actions intelligently. Let's dive into the if, else, and elif statements. The if statement is your program's most basic decision maker. It executes a block of code only if a given condition evaluates to teacher. For example, if age 18.print, you are an adult.
Right.
A simple eligibility check. If the condition isn't true, that print statement just doesn't happen.
Exactly. And building right on that, the else statement provides that essential alternative path. If the initial if condition evaluates it to false, the code block indented under else is executed instead. So, extend your example. If age 18.print, adult.else.print, minor. This creates a clear binary choice. Your program takes either the adult path or the minor path, never both.
Right. But what if you have more than two possibilities, like maybe different categories based on age? That's where elif comes in, which is just short for else if. You can chain multiple elif statements together after an if to check a series of conditions. They're checked sequentially in order from top to bottom. For instance, think about a grading system. If score equals 90, print A, then maybe elif score equals 80, print B, elif score equals 70, print C, and so on. Python will execute the code block for the very first condition that evaluates to true, and then it skips the rest of the entire if, elif, else chain. This allows for a really precise, cascading series of decisions, ensuring only one specific path is taken.
You can also nest these conditionals. That means putting if statements inside other if or else blocks. This allows for more complex sort of hierarchical decisions. For example, if age equals 18.Tiffy has license.print, eligible to drive. Here, the license check only happens if the age check passes first. It allows for highly specific, multi-layered conditions. However, This raises a really important point for good coding practice. While nesting is powerful, deeply nested conditionals, if inside if, can quickly make your code incredibly difficult to read, understand, and maintain. It becomes a tangled mess. If you find yourself with many levels of indentation, that's usually a strong signal you should probably refactor your code. A common and highly recommended technique to simplify this kind of complex logic is using what are called early exit or guard clauses. This basically means you check for failure conditions or prerequisites right at the beginning of a function or code block. And if those conditions aren't met, you exit early maybe by returning from the function. This keeps the main successful logic flatter and much easier to follow.
It avoids that deep arrowhead pattern of indentation. So instead of, say, if condition 1, if condition 2, if condition 3 dot do something, might write something like, if not condition 1, return. If not condition 3 dot return, do something. See how much flatter that is.
Ah, okay. So it's about making the code less like a maze and more like a clear, direct path, right? Yeah. That makes so much sense for readability and just figuring out what's going on later.
Exactly. It's all about clarity and maintainability in the long run. And beyond early exits, other good practices include maybe using Boolean variables to store the result of a complex condition first, just for readability, like is adult, age changes 18 if it's adult.
Yeah.
And of course, adding comments for a particularly complex logic to explain the intent behind your decisions is always helpful.
Okay, great advice. Now that we know how to make decisions and direct these single paths, what about when we need to do something over and over again? Repetition is key in programming. Or what if we have a block of code, a specific task, that we want to use repeatedly throughout our program without just copying and pasting it everywhere? That's where loops and functions become absolutely indispensable tools. For repetitive actions, we have looping structures. Let's start with the for loop. The for loop is really your go-to for iterating over sequences. That could be items in a list, characters in a string, or maybe numbers generated by the range function. You can easily loop through something like fruits, apple, banana, and process each fruit, or loop through each character in a word is Python. It's incredibly intuitive for processing collections element by element.
And that range function you mentioned is often used hand in hand with for loops. It's incredibly flexible. If you just use range stop, say range 5, it generates numbers from 0 up to, but not including stop. So 0, 1, 2, 3, 4, range start stop lets you specify a starting point. So range 2, 5 would give you 2, 3, 4. And range start stop step lets you specify an increment value dot range 0, 10, 2 would give you 0, 2, 4, 6, 8. This is your go-to tool for iterating a specific number of times or generating sequences of numbers with a particular pattern. It's Python's clean way to handle iterative counting without managing index variables manually. Now, within both for and while loops, you have these powerful flow control statements. Break and continue. Break immediately terminates the loop entirely. It just jumps out, even if the loop's condition hasn't been fully met or you haven't processed all the items yet. Continue, on the other hand, skips the rest of the current iteration and immediately proceeds to the next item in a for loop, or reevaluates the condition in a while loop. For example, you might break out of a search loop once you find the specific item you're looking for, saves computation. Or you might use continue to skip processing certain invalid values you encounter in the sequence.
Okay, those make sense. But you mentioned something about an optional else clause for loops earlier. That sounds a bit weird. Can you give us a really clear scenario where that's actually useful, maybe save some boilerplate code?
That's a fantastic question. And you're right, it often feels counterintuitive at first glance, and it's definitely an overlooked nugget in Python. The optional else clause that you can put on a for loop executes only if the loop completes normally. That means it goes through all the items in the sequence without encountering a break statement. This is incredibly useful, primarily for search operations where you need to know if you actually found the item you were looking for, or if you just exhausted the entire sequence without finding it. Instead of the common pattern of setting a flag, like found flag, false before the loop, then updating it inside if you find the item, and then checking the flag after the loop, you just use the else clause. Look at this pattern.python.for, item in my list, if item target value, if item target value.print, not if item, target value.break. Hashtag exit the loop since we found it.
Hashtag this else belongs to the for loop, not the if. Print item not found in the list.
See? The else block only runs if the break was never hit. It clearly differentiates between finding an item and not finding it, all without needing that extra flag variable. It's a very Pythonic way to handle these common search scenarios and can make your code more concise and arguably more readable once you understand it.
Ah, okay. That makes perfect sense now. It's tied to whether the break happened. Very cool. All right, then there are while loops. These repeat a block of code as long as a specified condition remains true. Now, it's crucial absolutely crucial here to make sure that whatever the condition is, it eventually becomes false. Otherwise, you'll create one of those infamous infinite loops and your program will just hang forever. For example, count equals 0, while count 5, that print count plus 1. That will print numbers 0, 1, 2, 3, 4, and then stop because count becomes 5, making the condition false. That count plus EL1 is essential. And just like for loops, break and continue work similarly inside while loops. And while loops can also have an optional else clause that executes if a loop condition becomes false naturally without hitting a break.
Exactly. So when choosing between for and while loops, you really need to consider the nature of your task. If you know the number of iterations in advance, or if your main goal is to go through each item in a sequence, like a list or string, a for loop is usually more appropriate. It's often considered more Pythonic for these cases because of its clarity and conciseness. Think processing every line in a file or every customer in a list. If, however, you need to repeat something until a specific condition is met and you don't know how many times that will take in advance, then while is your friend. Classic examples are reading user input until they enter a valid value, or maybe repeatedly trying an operation until it succeeds, like waiting for a network connection to become available. While loops are fantastic for that kind of condition-driven repetition.
Okay, perfect distinction now. This is where things get really transformative for writing larger, more organized programs. Introduction to functions, modularizing code. Functions are honestly a complete game changer for writing clean, organized, and maintainable code. They're fundamental. They let you encapsulate a specific block of logic, a task, give it a meaningful name, and then you can call that logic, execute that task whenever you need it throughout your program just by using its name. No rewriting the same block of code over and over. This promotes reusability, drastically reduces redundancy, and makes your programs infinitely easier to manage, to debug, and to expand later on. They are truly the backbone of structured programming.
Well said. And you define a function using the def keyword. It's followed by the function name you choose, and then a parentheses. Inside the parentheses, you can list parameters, like def add x, y. These parameters, x and y in this case, act as placeholders. They represent the values the function will receive when it's actually called or invoked. Think of them as the inputs the function needs to perform its specific task. It's a bit like giving ingredients to a recipe. The function is the recipe, the parameters are the ingredients it needs.
Right. And when it comes to calling functions, actually using them, you can pass the necessary information, the arguments, in different ways. Positional arguments are the most common. This means the order you provide the arguments in matters. Python matches them to the parameters based on their position. So if you call subtract 10, 4, and the function is def subtract AB, then A gets 10 and B gets 4. Keyword arguments are more explicit. Here, the name matters, not the position. You specify which parameter receives which value using the parameter name. For example, divide, numerator 20, denominator 5. This improves readability quite a bit, especially for functions that have many parameters where remembering the order is tricky. And there's a crucial rule if you decide to mix them. Positional arguments must always come before any keyword arguments in the function call. You can't put a positional argument after a keyword one.
Good point. And another thing that significantly increases function flexibility is using default parameter values. This allows you to define a default value for a parameter right in the function definition. This default value will be used if the caller doesn't explicitly provide an argument for that specific parameter when they call the function. For instance, def power base exponent 2. That exponent 2 sets a default. So if you call power 3, Python sees you only gave one argument base, so it uses the default for exponent, calculating 3 squared, which is 9. But if you call power 3, 3, you're providing a value for exponent, so it overrides the default and calculates 3 cubed, which is 27. This makes functions much easier to use in common scenarios where you might often want the default behavior while still allowing for full customization when you need it.
Makes sense. Very flexible. And when a function is done doing its work, it can give something back, right? It can return values. A function can return a single value using the return keyword, like return some result. It can also return multiple values. And when it does this, Python neatly bumps them up and actually returns them as a single tuple. For example, if you write return name, age, the function technically returns one thing, a tuple containing both the name and the age. And this often surprises beginners, but a function that doesn't have an explicit return statement anywhere inside it, it still returns something. It implicitly returns none. None is Python's special value that represents the absence of a value. So if your function just finishes without hitting a return, the caller gets none back.
Absolutely. Understanding none and how functions return values, including implicitly returning none, is really key. And speaking of clarity and understanding what functions do, we absolutely have to emphasize the importance of docstrings for function documentation. These are multi-line strings, usually enclosed in triple quotes, docstring goes here, placed immediately after the def line, before any code inside the function. Good docstrings are like little instruction manuals built right into your functions. They should clearly explain what the function does, what its parameters represent, including their expected types, often, and what values it returns. They aren't just for humans reading the code either. Python tools can actually read these docstrings to automatically generate documentation websites. And integrated development environments, IDEs, can display them as helpful pop-up hints when you're calling the function. They make your code understandable for anyone reading it, including your future self, 6 months down the line when you've forgotten the details. Honestly, good docstrings save countless hours of head-scratching.
Totally agree. Essential for maintainable code. Okay, so we've covered the individual pieces of data, how to operate on them, how to make decisions with IOs, how to repeat actions with loops, and even how to bundle logic into reusable functions. But what if you have a collection of data, not just one name or one number, but maybe a whole list of names, or a complex record of related information? Python offers some incredibly powerful built-in ways to organize and structure this kind of collected data. Let's dive into some of the most fundamental data structures. First up, probably the most common one, lists. Think of a list like a dynamic ordered shopping list. You can add items, remove items, change items at any time after you've created it. The key word here is mutable, meaning you can change their contents after creation. You create them using square brackets, S, and the items inside are separated by commas, like my list, apple, banana, cherry.
Exactly. And you access the elements inside a list using their index, their position. Crucially, indexing starts at 0 for the very first item. So mylist0 would give you apple, mylist1 gives banana, and so on. Python also supports negative indexing, which is really handy. It counts from the end of the list. -1 refers to the last element, cherry in your example. -2 refers to the second to last, banana, and so forth. And because lists are mutable, modifying elements is as simple as assigning a new value to a specific index. Like -0 grape would change the first item from apple to grape.
Right. And lists have a whole bunch of built-in methods for adding and removing elements, giving you a lot of flexibility in how you manage them. You can append an item, which always adds it to the very end of the list. You can insert index element to put an item at a specific position, shifting other elements down. Or you can extend a list with all the elements from another iterable, like another list, effectively merging them together. For removing elements, you have options too. There's remove value, which finds and removes the first occurrence of a specific value. There's pop index, which removes the element at a specific position. And importantly, pop also returns the item it removed, which can be useful. If you don't give pop an index, it removes and returns the last item. You can use del mylist_next to delete by index without getting the item back, or you can use clear to just completely empty the entire list, remove all its elements.
Yeah, the choice between remove, pop, or del really depends on your specific needs at that moment. Do you know the element's value you want to remove? Use remove. Do you know its position? Use pop or del. Do you need to actually get the removed item back to use it for something else? Then pop is your tool. Beyond just adding and removing, lists have other really useful methods. Index helps you find the position of the first occurrence of a value. Tent tells you how many times a value appears in the list. Sort will order the list in place, meaning it modifies the original list, reverse the order of elements also in place. And copy creates what's called a shallow copy of the list. This is crucial if you want to modify a copy without affecting the original list, preventing unintended side effects. Now, a truly Pythonic and often more efficient way to build new lists is by using list comprehension. This is a concise syntax for creating lists based on existing iterables. It's often much more readable and sometimes even faster than writing out a traditional for loop with append calls inside, especially when you're filtering or transforming elements.
For example, squares equals by 2 for x in range 10. That single elegant line creates a new list containing the squares and numbers from 0 to 9. You can also add conditions right inside the comprehension, like evens v equal x for x in range 10 if x plus 2 equals 0 to 9. This creates a list containing only the even numbers from 0 to 9. It's a really powerful tool for writing succinct and expressive code when dealing with lists.
Definitely powerful. And list slicing is another incredibly powerful feature for working with lists. It's kind of like taking a cookie cutter to your list to get just the part you want. The syntax is list_start.stop.step. It allows you to extract portions of a list, and importantly, it creates a new list containing just that segment of the original. The start index is included, but the stop index is not included. Step lets you skip elements. For example, mylist.3 gets the first three elements, indices 0, 1, 2. Mylist 2.5 gets elements from index 2 up to, but not including, index 5. And a super cool, very common trick is mylist-1. That step of -1 reverses the entire list in one go, creating a new reverse list.
Yes, and crucially, as you said, slicing normally creates a new list. This is really important because it prevents you from accidentally modifying the original list when you just wanted a piece of it. It helps preserve data integrity. However, slicing can also be used for in-place modification, which is interesting. You can assign a new iterable, like another list, to a slice of an existing list. For example, mylist 1.4 equals 10, 20, 30. This doesn't just extract elements. It actually replaces the elements within that specific range, indices 1, 2, and 3 in this case, with the new values. So it's a versatile operation for both extracting parts and modifying existing lists without needing explicit loops sometimes.
Okay, lists are fundamental. Now let's explore tuples. You mentioned these briefly when talking about function returns. Tuples are very similar to lists in that they are ordered collections of items. You can access elements using indices just like lists. But there's one absolutely key difference: immutability. This is where it gets really interesting. Tuples are like lists that you cannot change once they're created. You define them using parentheses, like my tuple, 1, 1, apple, true. Once that my tuple is defined, you cannot add new elements, you cannot remove elements, and you cannot modify any of the existing elements. It's fixed.
Right. And the implications of immutability for tuples are significant and offer distinct advantages over lists in certain situations. First, there's data integrity. Because their contents cannot be altered after creation, you can absolutely rely on the data stored in a tuple, never accidentally changing somewhere else in your program. This is a huge advantage for representing fixed collections, like geographical coordinates point 2 past 10, 20. You wouldn't want those changing. Or maybe database records read from a source, or configuration settings that should remain constant throughout your program's execution. Second, and this is often a big aha moment for people learning Python, is hacheability. Think of it this way. To use something as a key in a dictionary or as an element in a set, which we'll get to, Python needs a consistent, unchanging way to instantly calculate a unique identifier for that item, like a fingerprint or a fixed address. This identifier is called a hash. Because tuples are immutable, their contents never change. They can have this stable, unchanging fingerprint. They are hashable. This makes them perfect candidates for use as keys in dictionaries, especially if you need a compound key like Alice Smith, representing a unique person, or for storing them efficiently inside sets. Lists, being mutable, cannot be used as dictionary keys or set elements because their fingerprint could change if the list is modified, breaking the lookup mechanism. So mutability enables hashability, which is crucial for dictionaries and sets.
That analogy of a fixed fingerprint or street address for hashability really clears up why immutability is so important there. Makes perfect sense. Tuples also shine with things called tuple packing and unpacking. Packing is just the act of creating a tuple, often done implicitly just by putting values separated by commas, like my data equals 1, 2, 3. Python automatically packs that into a tuple. Unpacking is the reverse, assigning the elements of a tuple directly to individual variables, like x, y, z with my tuple. The number of variables on the left must match the number of elements in the tuple. This is incredibly convenient, especially, as you mentioned earlier, for assigning multiple return values from functions. If a function returns name, age, you can just write username, userig, get toStringinfo. Very clean.
Absolutely. And unpacking has some extra flexibility with the operator, sometimes called the start expression. You can use it to collect multiple remaining elements during unpacking into a single list. For instance, AB, res, 1, 2, 3, 4, 5. Here, A gets 1, B gets 2, and res becomes a list containing 3, 4, 5. Very useful when you only care about the first few items. And you'll often see the underscore used as a variable name during unpacking, like name, city equal user data. This is a common convention in Python to signal that you are intentionally ignoring that specific value, the middle one in this case. You don't plan to use it. Real-world use cases for tuples are everywhere, as we've touched on, representing coordinates, maybe RGB color codes like 25500 for red, fixed data records, and probably most commonly, returning multiple related values from functions, which Python elegantly bundles into that single immutable tuple object.
Okay, immutable tuples. Got it. Moving on to another incredibly useful structure, dictionaries. Think of dictionaries as unordered collections of key value pairs. They're much like a physical dictionary where you look up a word, the key, to find its definition, the value, or like a phone book where you look up a name, key, to find a phone number, value. The crucial things here are keys must be unique within a dictionary, and keys must be immutable, hashable, so strings, numbers, or tuples work great as keys, but lists don't. The values, however, can be of absolutely any type, numbers, strings, lists, even other dictionaries. You create them using curly braces with key-value pairs separated by colons, like this. Student, name, Alice, age, 20, major, computer science.
Right. And there are two main ways to access the value stored in a dictionary, with an important difference. You can use direct square bracket notation, like student name. This returns the value associated with the key name, which is Alice. But be warned, if the key you ask for, name in this case, doesn't actually exist in the dictionary, this method will raise a key error which can crash your program if you don't handle it. The safer, often preferred way, especially if you're not 100% sure a key exists, is to use the get method. For example, student.getAddress, NA. How get works is, if the key address exists, it returns the corresponding value, just like the square brackets. But if the key does not exist, instead of crashing, it returns none by default. Or if you provide a second argument like NA, it returns that default value instead. This elegantly prevents your program from crashing due to missing keys, and gives you explicit control over how to handle missing data. It's a crucial distinction for writing robust code that deals with potentially incomplete data.
That .get method sounds much safer for general use then. Good tip. And you can easily add new key-value pairs to a dictionary or modify the value associated with an existing key just by using assignment with square brackets. Like student GPA equals 3.8 would either add a new GPA entry or update the existing one. To remove elements, you can use del student age to remove the key-value pair associated with the key age, or you can use student.popMajor, which removes a major entry and also handily returns the value that was removed. Computer science in this case, which can sometimes be useful.
Exactly. And iterating through dictionary is also very flexible. You often don't iterate through the dictionary directly, but through specific views it provides. Keys gives you a view object containing just the keys, .values, gives you a view of just the values, and .items gives you a view of key-value pairs returned as tuples, key value. You typically use these in for loops, like for key in student.keys or for key value in student.items. And just like lists, there's also dictionary comprehension. It provides a concise syntax for creating dictionaries, similar to list comprehension. For example, x by 2 for x in range 5 would create the dictionary 0, 0, 1, 1, 2, 4, 3.9, 4, 16 in one line. Membership testing checking if a key exists is done very efficiently using the in operator, like name and student. This returns true or false, and is much faster than iterating through all keys yourself. Practical uses for dictionaries are incredibly diverse. They're fundamental for things like configuration settings, representing JSON data, counting word frequencies in text, simple phone books or user profiles, grouping related pieces of information together under meaningful names. They're everywhere in Python.
Okay, one more fundamental data structure to cover today, sets. Sets are also collections, but they have two key characteristics. They are unordered, meaning the items don't have a fixed position or index, and they contain only unique elements. So if you try to create a set like 1, 2, 2, 3, 4, any duplicates are automatically removed during creation, and the resulting set would just be 1, 2, 3, 4. The order isn't guaranteed either. They are fantastic when you only care about the presence or absence of an item, not its order or how many times it appeared.
Right. And just like dictionary keys, the elements you store in a set must be hashable. That means they must be immutable types like numbers, strings, or tuples. You cannot put mutable objects like lists or dictionaries inside a set for the same reason you can't use them as dictionary keys. Their fingerprint needs to be stable. You usually create sets using curly braces, just like dictionaries, but without the colons separating key-value pairs. So hello 1, hello 3.14 creates a set. But crucially, remember this common gotcha. Using empty curly braces creates an empty dictionary, not an empty set. If you need an empty set, you must use the set constructor function. My empty set equals set. The set constructor is also incredibly useful for converting other iterables, like lists, into sets. This is actually the simplest and most efficient way in Python to remove duplicate elements from a list. Just convert it to a set and, if needed, back to a list. Uniqueless list set original list. Where sets truly shine, though, is with their powerful built-in mathematical set operations. These are incredibly efficient, often implemented at a low level for tasks like finding common elements between two collections, or identifying what's unique to one group versus another. These include union, or the operator, for combining all unique elements from both sets. Intersection, for finding only the elements that are present in both sets. Difference, or length, for finding elements present in the first set but not in the second. And symmetric difference, or for finding elements that are in either set, but not in both. You can also efficiently check for relationships like is subset, or see if all elements of one set are contained within another, or is superset, or for the reverse. For example, finding all unique users who visited both web page A and web page B is a simple and fast operation. Common users set A and set B.
Those set operations sound really powerful for data analysis tasks, and since sets are mutable, unlike tuples, but like lists and dictionaries, you can add elements after creation. You use add to add a single element. If the element is already there, add does nothing because sets only store unique items. Use update to add multiple elements from another iterable, like adding all elements from a list into the set. For removing elements, you have a couple of options with a key difference. Remove element will remove the element, but it raises a key error if the element isn't actually found in the set. Discard element, however, will also remove the element if it's there, but if it's not found, discard does nothing and doesn't raise an error. This can often be safer if you're not sure whether the element exists. And there's also pop, which removes and returns an arbitrary element from the set. Remember, sets are unordered, so you don't know which one you'll get.
Exactly. And just like lists and dictionaries, sets also support set comprehension, offering a concise way to create sets based on iterables. For example, by 2 for x in range 1, 6 would create the set 1, 4, 9, 16, 25. Practical use cases for sets are abundant. We've mentioned the super simple duplicate removal from lists. They're great for quickly finding common or unique items between different data sources. And another key use is incredibly efficient membership checking. Using the in operator, like element of my set, to check if an item exists in a set is extremely fast, much faster than checking for membership in a list, especially for large collections. This is because sets use that underlying hash table implementation we talked about with hashability, allowing for near and set lookup, whereas for a list, Python might have to check each item one by one. So sets are indispensable tools for data cleaning, analysis, in any situation where uniqueness and fast membership tests are important.
Wow. Okay, that was quite a journey. You've just taken, I think, a massive shortcut to becoming truly well-informed on the absolute essentials of Python. We've journeyed through Python's fundamental building blocks, starting with those core data types integers, floats, strings, and booleans. We explored how they interact through all those various operators: arithmetic, comparison, logical, and assignment. We saw how to direct your program's decisions using control flow with if, else, and elif statements. We discovered the power of repeating actions smartly with for and while loops, and learned how to modularize code efficiently using functions. And finally, we explored these essential data structures for organizing collections of data: the mutable lists, the mutable tuples, the key-value dictionaries, and the unique element sets. This comprehensive dive has really equipped you with Python's foundational toolkit. You're now ready, really, for pretty much any programming challenge that comes your way.
And understanding these foundational concepts deeply, it's not just about being able to write lines of code, is it? It's really about developing a robust mental model of how Python, and honestly, how any programming language, fundamentally processes and organizes information. It empowers you to think algorithmically, to break down complex problems into manageable parts, and ultimately to build more robust, more efficient, and more readable programs, regardless of how complex they get. It's that leap, isn't it? From merely using the tools to truly understanding how they work underneath.
Absolutely. So here's something maybe to mull over. Building on that idea of mental models and how Python works underneath, how does Python's foundational philosophy, this idea that pretty much everything is an object from a simple integer or a string right up to complex functions and data structures, how does that subtly influence the way all these core building blocks we've discussed actually interact? Does it make the language feel more intuitive, perhaps, or maybe more powerfully consistent in ways we might not immediately recognize when we're just focusing on learning the syntax? It's kind of a deep concept, but it really underpins much of Python's perceived elegance and power. Something to think about. Until our next deep dive, keep learning, keep exploring.